first results from the Muon g-2 experiment strengthen evidence of new physics. The first results from the Muon g-2 experiment at the U.S. Department of Energy's Fermi National Accelerator Laboratory have revealed that the fundamental particles called muons behave in a way that is not predicted by scientists' best theory to date, the Standard Model of particle physics. The strong evidence that muons deviate from the Standard Model calculation might hint at exciting new physics. This experiment is a bit like a detective story, said team member David Herzog, a University of Washington professor of physics and a founding spokesperson of the experiment. We have analyzed data from the Muon g-2's inaugural run at Fermilab and discovered that the Standard Model alone cannot explain what we found. Something else, perhaps beyond the Standard Model, may be required. The Muon g-2 experiment is an international collaboration between Fermilab in Illinois and more than 200 scientists from 35 institutions in 7 countries. UW scientists have been an integral part of the team through the Precision Muon Physics Group, constructing sensitive instruments and sensors for the experiment and leading data analysis endeavors. In addition to Herzog, current UW faculty and lead scientists involved include Peter Kamel, research professor of physics, Eric Swanson, a research engineer with the UW Center for Experimental Nuclear Physics and Astrophysics, or CENPA, Jarrett Casper, a research scientist, and Alejandro Garcia, a research professor of physics. The UW custom-built instrumentation would not have been possible without the extraordinary dedication and expertise of our CENPA technical staff, who work closely with our postdocs and graduate students, said Herzog. A muon is about 200 times as massive as its cousin, the electron. They occur naturally when cosmic rays strike the Earth's atmosphere. Particle accelerators at Fermilab can produce them in large numbers. Like electrons, muons act as if they have a tiny internal magnet. The strength of the internal magnet determines the rate that the muon processes in an external magnetic field and is described by a known number as the G factor. This number can be calculated with ultra-high precision. As the muons circulate in the Muon g-2 magnet, they also interact with a quantum foam of subatomic particles popping in and out of existence. Interactions with these short-lived particles affect the value of the G-factor, causing the muon's precession to speed up or slow down slightly. The Standard Model predicts that with high precision, what the value of this so-called anomalous magnetic moment should be. But if the quantum foam contains additional forces or particles not accounted for by the Standard Model, that would tweak the Muon G-factor further. The new experimental world average results announced by the Muon g-2 collaboration today are G-factor 2.0023318 for 12282, anomalous magnetic moment 0.001165920641. The combined results from Fermilab and Brookhaven show a difference with theoretical predictions at a significance of 4.2 sigma, a little shy of the 5 sigma or 5 standard deviations that scientists prefer as a claim of discovery, but is still a compelling evidence of new physics. Many of the sensors and detectors at Fermilab were constructed at UW, such as the instruments to measure the muon beam as it enters the storage ring and to detect the telltale particles that arise when muons decay. Dozens of scientists, including faculty, postdoctoral researchers, technicians, graduate students, and undergraduate students, have worked to assemble these sensitive instruments at the UW and then install and monitor them at Fermilab. UW scientists have also been involved in the theoretical work around the Muon g-2 collaboration. With these exciting results on our team, in particular our students, it is enthusiastic to push hard on the remaining data analysis and future data taking in order to realize our ultimate precision goal.